Assalamu alaikum. Bismillahirrahmanirrahim. My dear students, welcome you all. You know that due to COVID-19, your syllabus has been reduced. And in this reduced syllabus, your first year chemistry 11th chapter is of thermochemistry and only two topics, Hess's law and its related numericals, and Born Haber cycle have been included. So today's lecture is concerned with Hess's law and Born Haber cycle. In some next lecture, we shall try to calculate to solve the numerical problems or numerical questions. Dear students, what the Hess's law is? You are watching on the screen the definition of Hess's law. Hess stated this law in 1840. It states that enthalpy change in a chemical reaction is same whether the reaction takes place in single step or in several steps. Mathematically, sum of enthalpy changes for the cyclic process is zero. Dear students, just Hess's law want to say this is law of conservation of energy, that if reaction takes place in only one step and there is some change in energy, the same change in energy will take place when this reaction adopts another route, another course, and different steps are involved. The sum of all those steps which have been taken by this process in different route are equivalent to the enthalpy change that is taking place in a single step. That is simple Hess's law. Enthalpy heat changes at constant pressure. You may say, you know that H is equal to E plus PV. Next, here is an example shown. That is combustion of carbon to carbon dioxide. It may also be called as formation of carbon dioxide. So carbon solid, oxygen gas, they combine and give carbon dioxide product. Enthalpy change during this process is 393.5 kilojoules per mole. That is the amount of energy that is released during the combustion of carbon 1 mole to give 1 mole carbon dioxide. Reaction may take place in two steps. For example, reaction may take place in two steps. For example, here I try to highlight also. Here you find that this is one step which I have shown with the green line. This is this one is one step, and second one is two step, step 1 and step 2. So this has been further explained that carbon and oxygen is formed directly. Carbon oxygen combine to form directly carbon dioxide. I have shown with green arrow, that is in single step reaction is taking place. And at the right hand side, this reaction is taking place in two. For example, this is step 1 and this one is step 2. Now enthalpy changes of step 1 and 2 is equal to enthalpy change that takes place when this reaction happens in a single step. That is just explanation. I think that you should learn by heart these values as well. 393.5 kilojoule energy is released during one step. This is one step, single step equation. And if this reaction takes place in two steps, then the sum of enthalpy changes will also be equivalent to 393.5 kilojoules per mole. So that is the explanation of Hess's law with example. Next comes Born-Haber cycle. Whenever you have Born-Haber cycle, you must at the same time there should come in your mind that this is something related with lattice energy. So it is special application of Hess's law. And just which I have just told you, that if reaction takes place in single steps or more than one steps, enthalpy change is same is here. First of all, some introductory sentences have been given. This is special application of HESS'S law I have just told you to binary ionic compounds. Binary ionic compounds which consist of only two types of elements. It helps to calculate lattice energies of binary ionic compounds. M plus, for example, sodium cation, X negative, for example, chloride anion, or your syllabus is another Born Haber cycle, that is of magnesium oxide. It M plus may be Mg plus 2 and X minus may be O minus 2. So this extension of HESS'S law is very helpful in the determination of lattice energies of ionic compounds. What the lattice energy is? Something energy change that takes place during the formation of something from its gaseous ions. Change in energy that takes place when separated gaseous ions are separated ions also are packed together to form 1 mole of ionic solid is called lattice energy. This process is always exothermic. Another way of defining the lattice energy is energy required to convert 1 mole of the solid compound into gaseous ions. Of course, this would be endothermic process. And in a second equation here, this one, this can be explained that sodium chloride is solid and gaseous sodium ions and gaseous chloride ion. Now the value that is given in your textbook, that is 787, and that I have mentioned here separately, 787, this one. This has been explained. You can find on the right hand side that it is solid sodium chloride, that is cations and anions have been packed in crystal, and when this arrow is indicating energy is being absorbed. When energy is absorbed, they are converted into gases, and this right hand side is showing gaseous ions. So these are gaseous ions. You may call, if this is crystal is of sodium chloride, then sodium may be represented by smaller cations, that is purple in color, and chloride anions are bigger, so they are shown by green colors. So this right side, this solid crystal is separated into gaseous ions. Amount of energy that is absorbed during this process is called lattice energy. Next comes another way to explain this. Now this is according to your textbook. You find here that on left hand side, gaseous separated ions are, which I have encircled in blue color, and on the right hand side, which is again I have encircled, these gaseous ions are packed in the crystal. During these red lines are indicating the energy is being released, and this process is always exothermic. Negative sign is shown here. So X kilojoules. For example, these are purple are sodium cations. This one. And these green are chloride anions, they have been packed together into, then the amount of energy released is 787 kilojoules. In that case, X would be 787 kilojoules per mole. Again, this has been explained in another slide. Separate gases ion on left hand side, energy given off, that is energy is evolved, and crystal lattice forms, which has been shown on the right hand side. These things have been further explained in the form of text here. You can find here that on the right hand side you have this one, these are gaseous ions. These are gaseous ions. Sodium ion gaseous form, chloride ion gaseous form, written here. Sodium chloride solid, lattice energy 787 according to book. Sign is important. Standard state product, I am going to define standard state shortly. Remember to state the units, that is kilojoules per mole. Everything okay here? Next slide. Standard conditions. What are standard conditions? 1 atm pressure, that is standard condition. 1 atm pressure, that is 760 torr, 1 bar, or 101 kilopascal. SI unit is kilopascal. And 298 Kelvin, second condition, that is 25 degrees. That zero, not zero, but degree here is not to read it 250, 25 degrees Celsius, and it is usually written in Kelvin reading, so 298 Kelvin, and 1 molar solution, that is the standard conditions. Next. Born-Haber cycle of sodium chloride, that is part of your syllabus here. In case of sodium chloride, the reaction may takes place in single step. For example, this one is on the left side. This, you start here, and sodium solid, chlorine gas, and you get sodium chloride. That is the reaction taking place in single step. Same reaction is broken in different steps. For example, this is first step, that is enthalpy of sublimation, that is sodium solid is converted into sodium gas, and the next is this sodium atom loses one electron, and that is called ionization energy, and is converted into sodium cation, that is second step. Third step is this chlorine molecule, it is broken into its constituent atoms. So two atoms combine together through covalent bond, and in these chlorine molecules are converted into chlorine atoms here. And these three steps are, this is one, this is second one, this is third one. These are endothermic, so they are shown in the upward side, because you are representing energy with upward arrow here. This is energy, upward arrow is being represented. And next, when electron is picked up by chlorine atom, that is called electron affinity. That is fourth step, that is on right hand side. And since energy is released during process, 350 around 349 kilojoules, so you have shown this in the downward side, because energy is now becoming less in case of chlorine atom. When it picks one electron, that is called electron affinity, it releases energy. Now here you have on the, I try to highlight it's with some other color. For example, this is with green. These are sodium cations and chloride anions. These are in gaseous state. They are separated. They are widely separated from each other, and these are packed together into crystal. And same product which was obtained previously, you shown with blue color sodium chloride, same is with green color, and sodium chloride crystal is obtained. So the reaction which is taking place in single step, that is this one, and the reactions which are taking place in more than first, right, starting from here, going this way, coming up to here sodium chloride, the enthalpy changes is same, and that is the just HESS'S law. So if you know any all values except one, you can calculate the value of that unknown, that may be electron affinity, that may be lattice energy. Okay, comes to next. Now we have some standard definitions here. For example, enthalpy of formation is although this is not part of your reduced syllabus, but I think that you must know in order to understand the topics clearly and to have clear concepts. Enthalpy of formation is enthalpy change that takes place when 1 mole of a compound is from its elements. When 1 mole of compound is formed from its elements in their standard states under standard conditions, that is called standard enthalpy of formation. Enthalpy of atomization, when 1 mole of gaseous atoms is formed from element under standard conditions, is called enthalpy of atomization. Since solid metal when vaporizes, it is converted into atoms, so in case of sodium and magnesium, enthalpy of vaporization has been written instead of enthalpy of atomization. Similarly, we have definition of ionization energy. 1 mole of electron is removed from 1 mole of gaseous atom under standard conditions, that is called enthalpy of ionization or ionization energy. For example, sodium, when loses 1 electron, this energy change during this process is called ionization energy. Removing electron from atom is always an endothermic process. Energy must be supplied to overcome the attraction of the electron to the nucleus. The more electron that are removed, the more endothermic process will be. Similarly, another definition is electron affinity. Enthalpy of electron affinity or just electron affinity. 1 mole of electrons is added to 1 mole of gaseous atoms to form anions under standard conditions. First electron affinity is always negative. Second electron affinity is positive because it has to overcome the repulsion of already negatively charged anion during the addition of electron. Now, Born-Haber cycle, which is of magnesium oxide, is given in your data is given in your book, and you are to draw and to calculate lattice energy. I have tried to solve it this problem too. This self-check is 11.6 of your textbook. Draw a complete Born-Haber cycle for the formation of magnesium oxide. Calculate the lattice energy for magnesium oxide from the following data. This data has been given, and in the next slide you can watch the lattice energy may be described in following steps. Different steps have been given. First step is magnesium solid. This one is the first step. Magnesium solid to magnesium vapors. Second is ionization energy. Magnesium atoms are converted into magnesium ions. That is enthalpy of atomization. Oxygen atoms are formed from oxygen molecule. Next electron is picked up by oxygen and converted into O-1. That is exothermic process. But in the second case, when O-1 picks up 1 electron, gains 1 electron, that is energy is released during this process in order to overcome the repulsion. Energy is to be absorbed during this process. So O2 O minus 2 from O minus 1 is endothermic process. So step 5th is endothermic. Now last step, magnesium plus 2, they are on left side, and O minus 2, these are gases and they pack together into crystal. That is, this one is lattice energy. So this is lattice energy. This is to calculate. And net reaction is magnesium solid, magnesium oxide, and gives magnesium oxide product. Magnesium solid O2 and gives magnesium oxide. This problem has been solved here. You have that enthalpy of formation is equivalent to all those enthalpy changes, and you are to calculate this one, that is lattice energy. So by using lattice this equation, that is Hess's law. This is enthalpy change during single step. These are different steps, and sum of these enthalpy changes according to Hess's law is equal to enthalpy change that takes place in single step. So you can calculate in this way lattice energy of magnesium oxide as well. Second part of the question was to draw Born-Haber cycle. So this has been drawn. This is single. This reaction is in single step. This is one step. This is second step. This is third step. This one is fourth step, and this one is, which is going above, is 5 step. Now when electron is gained by O minus 1, then the incoming electron feels repulsion. In order to overcome so due to this repulsion, energy is in order to overcome this repulsion, energy is required, and that is why the second electron affinity value is positive, and this electron affinity value is positive, and this process is endothermic. Now you are to convert magnesium plus to oxygen minus 2 into magnesium oxide, and this energy, you know that this energy is called lattice energy. So that is Born-Haber cycle. Thank you very much for watching this video. I hope it would be helpful for you. Thank you. Allah Hafiz. Assalamu alaikum. Pakistan Zindabad.